do a favor of going to Amazon.com and write some reviews on it. Okay? So the Amazon site has some reviews, but it has all the code snippets. But what you need is actually given you as a seed code, so that's what we're going to go through now. And they have all these things. Okay, so I gave you three programs. Okay, so the first program really generates the public key and private key. Okay, so if you read the project description, I asked you to run it twice. Okay, so you can use this code to generate the public key and private key, which means you don't need to implement RSA. RSA is already implemented in this. Okay, it's a very simple implementation. Okay, and so the idea is this: you, as I show here, if you generate this program, or run this program, it will generate you the public key and private key. Okay, the way it works is this: it needs okay, let's go through this line by line. So, there are two random number generators I'm creating. So, this is one way you can create random number generators in Java. Okay. So, this is actually a seed value. The system time I normally use as a seed value because it's bound to be different every time you run your program. Okay. And two different seed values, so I multiply the system time by 10 so that there are two different seed values. Okay. Now, remember, I always try to remember what we did in class. You are given this P and Q, and then you wanted to choose your encryption key as a starting key, right? And I said choose above 10, isn't it? 10 or above. So like that, you guess what you want to be, or you enter your public key, what you want as a possible public key. It may not be a public key, but you have the privilege of at least telling this is what I want to be my public key. Okay? If it is possible to have that as your public key, for example, when I run it, I say 34 is what I want as my public key. If it is possible, it will have 34 as the public key, or it will increment 35, 36, 37, and so on until the value can be your public key. Right? So, those P and Q are randomly generated here. We use a class called big integer in Java. So to work with all those big integers like 100 digits, 200 digits long, we kind of import this big integer class. So I don't know how many of you have used this. I always suggest you to go through this API. So you go through the Oracle or Sign, whatever it is. These are all the classes. It's like a library where you can really refer to all the classes and methods. So one of them is a big integer class, and if you click on this, you can see all the methods and constructors in this class. So this will be like a reference for you. What are the methods? You want more explanation of all those methods, you can use this. Okay? And even the socket classes, everything will be here. Okay? So just Google up Java API and you can get it. So what I'm doing is, this probable prime method, and it takes two arguments, 32 is like, stands for 32 bits. So I'm generating a random integer which is 32 bits long. Okay? and the rand1 is the random number generator that's part of this. So if you feed this, it's going to generate a prime integer. If the name of the method says probable prime, which means the big integer that's generated is probably a prime, not definitely a prime. But the probability of it being a prime is very high. If you look at the probable prime method here in the API, and you click on it, you see here returns a positive integer that is probably a prime with a specified bit length. The probability that it is not a prime, which means the composite means opposite of prime. Okay? The probability that it is not a prime is 1 over 200, which means it's very likely to be a prime. 1 over 2 to the power 100, not 200, 1 over 2 to the power 100. You see how small it is? This is the probability that the big integer that is generated is not a prime. So it's very likely, 1 minus of this is the probability that it is prime. So it's very likely to be prime. You know, if you remember the P and Q, you want them to be prime, right? RSA. So that is how you generate your P and Q to be prime in big integers. So I here suffix them as big P, big Q. So these are your P and Q. And then to multiply them, you know, remember the sequence, you generate PQ and then what you do?
Go to
You multiply to get N.
Right, so you get that N to get P times Q, right? So you do that, so generate P and Q and then you do N equals P times Q and then what you do? You compute P minus 1 times Q minus 1, right? And that's what we do as the next step. We compute P minus 1. So I compute P minus, okay, so to multiply them, this is the method you choose. And this is an object actually. The big int is a class and these are all objects. So I call the multiply method on one of the objects, on the P object, and pass the Q as the argument. So you are basically multiplying P and Q. Yes? The 32 means 32 bits. You know, big integer you want it very long. So you are generating a 32-bit long integer. So then I want to get this P minus 1. So you call the subtract method on this big integer object, and you have to work with objects here. So this 1, you know, the P minus 1, I'm passing it as an object. This 1 is passed as a big integer. That's what the new big integer 1 does. Okay? So this 1 is a big integer. You subtract from P. So this is P minus 1 now. Alright? And then Q minus 1 for same thing. And then you multiply them. P underscore 1 is P minus 1. Similarly, Q underscore 1 is Q minus 1. So you do a multiplication. P minus 1 times Q minus 1. So now, it's what is the next step? You want to generate your public key. Remember there I said choose, what's the next step in our slide? Choose your key, the encryption key to be relatively prime. To what?
Does it have to test it first?
You have to test it, that's what we are doing there in the
Okay.
code. So relatively prime
To the value you get.
which value?
Q.
What you get from the third
Yeah,
rule.
to P minus 1 times Q
Q.
minus 1. So what is the starting value of your key E? The one that you input to this program. So in this case when I run it, I pass 34, right? So that is assigned to be my public key. So this is my starting value which I get as input from the user. Okay, public key input, I usually use the command line argument, you can use scanner or whatever else you prefer to get input. So now, we use a while loop because we are not sure when we will stop. So it's an infinite while loop, but once I manage to find my right public key, I can stop. So what I do inside, you see this is an integer to start with, the public key, right? So I want to make it as a big integer, right? And how to test for relatively prime. I want the encryption key to be relatively prime to this, right? So which means the GCD of this, the encryption key, and this T minus 1 times Q minus 1 should be what?
One.
1. And that's what I'm doing there. And the GCD, see, this is very convenient. The big
That's what I was
integer
asking.
class also has a GCD method.
That's what I was asking when I said tested.
Right. So it has a GCD method that you can use. It's built in Java.
Okay.
So you call that GCD method on this product P minus 1 times Q minus 1, and the argument you pass is your public
I
key
hate this thing.
or candidate public key. If it turns out to be 1, so that's your GCD, right? If it's equal to 1, so this is how we test whether it is equal to 1 or not, because everything is object here, not scalar quantities. Okay? So if it equals to 1, you can break from the infinite while loop, which means you have found your correct public key. So otherwise you keep incrementing. So when you start with 34, and if 34 is not relatively prime to my P minus 1, Q minus 1, I keep incrementing it until I find a public key which is relatively prime. Yes?
So it's gonna increment for after whatever number you choose.
Right.
So if you choose 10, it's gonna go 10, 11, 12, 10.
Exactly.
Okay.
Exactly. So I break from the loop once I found my public key, and I am getting a big integer version of it by doing a new big integer. So this is my public key in the big integer format. Okay? So what is the last step then? Once you choose your encryption key, we have to choose your decryption key, and what's the rule for that? What's the rule for the decryption key?
Oh, the inverse. The inverse of.
Right, so the decryption key, here you can choose, here you have to find,
The MI.
yeah, what is your mind? The decryption
Multiplicative
key, which is
inverse.
D, which is a multiplicative inverse of the encryption key in class modulo P minus 1 times Q minus 1. Right? So you want to find a decryption key that is a multiplicative inverse of the public key, right? So the public key is what we found now. So the private key, you can't read it?
Mm-hmm.
It is the P minus 1 times Q minus 1.
Dr. Meg, is there a class for that?
Huh?
Is there a class for that?
Class?
Is there a multi, like you got
Yeah.
GCD?
No, everything is a method. So the class is big integer. Everything is a method now.
So like you found it, like there was a method for the GCD, there's a method for that?
Yeah. Method for multiplicating.
Yeah.
Right. You're talking about PQ instead of P minus 1, Q minus 1? Yeah, so you're telling this should be P times
just
Q
gotta pull
instead
back
of
on
P
back of my
minus
head.
1 times Q minus 1? You can get up.
When I saw the example, which happened last time,
Choose the key, the decryption key is a multiplicative inverse of the
oh,
11 mod 120. 120 is the P minus 1 Q minus 1. Okay. So how would you find the thing? There is a function called mod inverse that gives you the multiplicative inverse. Okay, so they have done, right, they have done everything for you. The only thing is it took me a long time to figure out how to do this. So now I'm giving it like a vanilla cake for you where you can see everything, but I have to figure out how to do this. And but once I figured out a big integer class, I went through all these functions, the description in here, then I figured out how to put everything together.
So you want us to run that program?
Yeah, I don't know whether this has a compiler. So yeah, you could run it like I showed here, compile it, and run it like pass this argument. Only argument you have to pass is the starting public key. And then let's go through this and complete. So this, you're calling the mod inverse method on the public key big integer and this passing this argument. So all it means is you're finding the multiplicative inverse of this guy in the class modulo this one. The multiplicative inverse of the public key in the class modulo p minus 1 times q minus 1. And the whole thing is going to return you what? The private key. Right? Because that's the rule. Find the decryption key, which is a multiplicative inverse of the encryption key in the class modulo p minus 1 times q minus 1. So that's going to return you the private key. Right? And that's your big key.
Excuse me.
So I print out, remember I said the encryption key is the public key comma n, right? N is p times q. And the private key is also this. So that's what gets printed out. The public key you see is so small, 37. But the n is this. It's 32 bits. Okay, so you can even go up to 64 bits if you want to. Okay, and then this is your private key, is so long. And this is same, the n is the same. You see, this is same as this. Okay, because it's the n on both sides. So if you see the project description, I would have asked you to run it twice. One set is for the sender. Sender has a public key, the corresponding n value, the private key and n value. Run it again and use that as the public and private key for the receiver. Because when you run your program, you are the sender receiver. So you run two programs, right? One is the sender and one is the receiver. So you need the public key of the sender, private key of the sender, equal to the public key and private key of the receiver. Right?
So you get the public key of one of, so you can run the second. You use that public key.
Yeah, so when you run it, right, typically you need two people to run your program, right? So that one person can just be the sender, the other person can just be receiver. But as a student, you're doing the project, you need to run both the sender and receiver, right? So you run on two different terminals.
Oh, okay. You're gonna open two different
Two
shares.
different command
Right.
windows.
Okay.
Run one as a sender and one as a receiver.
So it's like the sockets because you have the
Yes.
socket
No,
on one
yeah,
way.
that's
Yeah,
right.
that's like the sockets. Yeah. Okay.
So one guy will be the sender and another guy will be the receiver, right? So it's like when you don't have any brother to play with you, you play as right. So like that, you will be the sender and you also be the receiver. Yes.
So the private key, is it always the same?
That ain't gonna be hard to do.
Yeah, it's 32
It's the same as the
bits, so
socket program. I still got the
because of
socket
32
program.
bits.
Yeah, because
A little modification, it'd be
I'm
alright.
using a 64-bit.
You get a different length.
Yeah, the first one was 20, and the second one was 19. So, I don't know, maybe I should run it again. But I ran it
think
just twice.
if you change this to 64,
Because at first I didn't understand what it was weird. So I had
did you change that to 64?
no, I didn't.
Yeah, change that to 64.
Okay.
That's
one
what-
line?
The probable prime where you generate your P and Q, right?
Okay, and that's in the RSA.
That needs to be, that 32 means a 32-bit integer.
Okay.
Okay?
Oh, so you have to change it.
If you want to make it 64, change it there.
Oh,
Do you have to make it
No,
64?
no, I'm just telling you.
okay.
64 means it will be a long integer.
Oh.
I'm gonna keep it simple.
32 is good enough.
Yeah.
Okay? Alright, so now, let's see. So public key, private key is generated for you. So what this does is, this is basically doing the encryption. So the first code does the, generates the public key and private key. The second code shows you how to encrypt a character. Okay? So you input the public key and private key that you just generated, and you pass the n value. So these three correspond to the public key, private key, and the last argument is an ASCII value of some character that you want to encrypt, like how we did in examples, like 227 or 207 or whatever, right? And again, what is the thing? You do a mod, right? So if I want to encrypt a plain text, so you encrypt this with do a public key rise to public key mod n, right? This is how you encrypt, right? And then I believe I encrypt, yes. So you encrypt, you see, this is ASCII value. I'm getting the big integer version of the ASCII value, right? And then I do a mod power. So this is the modular exponentiation function. So this function does the modular exponentiation, mod power. And you call the ASCII value, the plain text, dot mod power pass the public key, and your n, mod n. So this is the exponent part and this is the mod n part. Okay? It uses the ciphertext. Okay? You can print it, and then to decrypt, what you do, the whole thing you have to, so this is the ciphertext. The ciphertext rise to the private key mod n should get you what?
The
plain
Right,
text.
plain text.
Right? So that's what I'm doing now. The ciphertext mod pow, the private key, comma big, the n value should get your plain text. Now the plain text you get to a big integer. So if you want to get the plain integer value of it, you can use the int value method to get the integer scalar portion of it, and you can print it. So that you, if you run it, like it will, you can pass the public key, the private key, and the third argument is the n value, and then the ASCII value. This probably is character A. So this is a ciphertext, and then when you decrypt, you get back a plain text.